Okay, so let's continue with our discussion. So you know, we are at the stage of trying to understand the meaning of open sets in the zariski topology, and I told you in the last class that an open set is always built up of so called basic, as a union of basic open subsets, and these basic open subsets are subsets which are given by the locus of non-vanishing of a single polynomial. Okay, they are called the basic open subsets. Now you see there is a very important property about open sets in the zariski topology, which is what stating which I ended the last lecture, and that was quasi compactness. Okay, so let me begin from there. Okay, so so here is a definition. A topological space is called quasi compact if given an open cover we can always find a finite subcover. Okay, so this is the definition of quasi compactness. In fact, see, if you study general topology, this is the definition of compactness. Okay, in general topology normally this is the definition we give for compactness of a space. The compactness is if you give me a collection of open subsets whose union equals the space, then from that collection you can extract a finite subcollection whose union will also be equal to the whole space. This is what it means when we say that in every open cover you can always find a finite subcover. Okay, and this should happen for any open cover. When I say an, of course it means any. So so if you want, maybe I'll modify this and to any, which is what I mean. So what does that mean? So if you write it in symbols, you know, that is, if x equal to union of u alpha, where or let me write u lambda in capital lambda, where each u lambda inside x is open, then there exists lambda 1 through lambda m finitely many indices from the set lambda such that x is just the union of these corresponding u lambda. So x is union u lambda I equal to 1 to m, and we say that the subcollection u lambda 1 through u lambda m is a finite subcover of the original cover which consists of the collection of all the u lambdas. Okay. Now of course each u lambda is an open subset. Okay. Now this is the definition of compactness in a topological space. Okay. This is the usual definition of compactness, but if you study topology you will always find that just compactness alone is not a very good property. Usually you should also have compactness with Hausdorffness, and the most good type of space is a space which is locally compact Hausdorff. Okay. These are the nice spaces on which you can do reasonably good topology. Okay. So but in algebraic geometry especially in connection with the zariski topology we don't use the word compact. Okay. The reason is I'll tell you the reason for that later, but the more important thing is that we use the word quasi compact. Okay. And so the first thing that I wanted to notice about this definition is that this is the definition of what a compact topological space is in general, but in the zariski topology whenever you are in algebraic geometry you always use only the word quasi compact, you don't use the word compact. Okay. And of course that should the technical reason for that is that compactness stands for something else, and even there this something else is not called compactness, it is given a different name, it is called properness or completeness. Okay. So the word compact itself is kind of not very suitable for a algebraic geometry. Okay. And another so you must remember that this quasi is especially in the case of the zariski topology. Now what I want to tell you is that if you now take K to be an algebraically closed field and you take affine space over K and you look at the zariski topology, then the topology itself is quasi compact. I mean the zariski topology is quasi compact for free, it's God given, so it's nothing special. Okay. But you can remember that when we study general topology compactness is a very special thing. Okay. So in Euclidean space a subset is compact if and only if it is closed and bounded. Okay. So if you take a subset of Euclidean space which does not have a boundary point then it cannot be compact, if it is not closed then it cannot be compact. So compactness means so many things when we study the Euclidean topology. Okay. That is Rn, okay, n dimensional real space with the usual topology. But as far as zariski topology is concerned, this compactness in the sense of every open cover having a finite subcover, that comes for free. Okay. So that is why we reserve the word quasi compact for that. So this is the last statement I made last time. So I should say, if you want proposition, the zariski topology is quasi compact. Okay, it's quasi compact. So let me write it. Okay. Now why is this happening? So the reason is actually it's because of the Noetherianness. Okay, it's actually because of the Noetherianness, which I'll explain as follows. So what I'm going to do is first is I'm going to say that this follows the proof of the proposition follows from a couple of lemmas. Okay, so here is so let me write that the proof follows from the following the next two lemmas. Okay, so so the first one, so here is the lemma, and that lemma, the lemma is that any Noetherian topological space is quasi compact. Okay. Okay, this is the first lemma, which says that you take a topological space that is Noetherian, then automatically it is quasi compact, alright. And in the Zariski topology is is Noetherian in the sense that if you take any affine variety, for that matter you take any closed subset, any algebraic set in affine space, then you know that it can be broken down. It has a Noetherian decomposition, and affine space is of course Noetherian. Okay, affine space, if you take affine n space over K, okay, which is just Kn with the Zariski topology, K an algebraically closed field, okay, then you know the affine space is a Noetherian topological space for the Zariski topology. That's just because that just translates to the Noetherianness of the ring of functions on the affine space, which is the Noetherianness of the polynomial ring in n variables, which you know is true because of Hilbert's basis theorem. Okay, so so I am saying that the quasi compactness just is a result of the Noetherian property. So how does one prove this? The proof is pretty easy. Proof is, well, what do I have to show? I'll have to show I have a topological space which is Noetherian, then I have to show it's quasi compact. So I assume that the topological space is called X. I assume that U lambda is an open cover for X. I have to cook up for U a finite subcover. I have to find finitely many indices lambdas such that the corresponding U lambdas, finitely many U lambdas, their union is also equal to X. Okay, that's what I'll have to do. So what I'll do is so let U lambda, small lambda and capital lambda be an open cover for X, that is X is union over lambda U lambda. Okay, I will have to show that there is a finite subcover from this collection for X. Okay, so what do? I do the following thing. I try to somehow make use of the hypothesis. My hypothesis is that it's Noetherian topological space. Now what is the definition of Noetherian topological space? If you recall, there are several definitions, equivalent definitions. One definition is perhaps the basic definition or the usual definition is that there is DCC for closed sets. That is, if you have a sequence of closed subsets, one becoming smaller and smaller, that is every next one contained in the previous one, then this sequence has to, at some point it has to stabilize. That means if it is a strict sequence, then it has to stop, and if you don't demand it's a strict sequence, then all the terms of the sequence become the same beyond a certain finite stage. Okay, this is the DCC, that is a descending chain condition for closed sets. Okay, and you know, when you put this condition for affine space, you know, affine space in affine space closed sets correspond to radical ideals in the polynomial ring, and therefore the descending chain condition for closed sets will correspond to the ascending chain condition for the corresponding ideals in the polynomial ring, which is true because the polynomial ring is Noetherian by Hilbert's basis theorem, and this is what gives you the fact that affine space is with the Zariski topology is a Noetherian topological space. So that's one definition, that there is DCC for closed sets. There are other definitions. The other definition is that since open sets are the complements of closed sets, okay, you can say that there is ACC for open sets. Okay, that's one equivalent definition. And then there is another definition of yet another equivalent definition, that is, given any non-empty collection of closed sets, there is always a minimal element with respect to inclusion. This is one more definition, equivalent definition of Noetherianness of the topological space, which in the case of affine space actually translates for the to the polynomial ring having the property that you give me any if you give me a collection of ideals, there is always a maximal element. If you give me a non-empty collection of ideals, there is always a maximal element. That is, for example, the ring theoretic definition of one of the equivalent definitions of a Noetherian ring. Okay, and then there is yet another so probably I'll try to use that. So I'll try to use the fact that in this, since this topological space is Noetherian, if you give me a collection non-empty, if you give me a non-empty collection of open sets, there is always a maximal element. So what I will do is, so I will have to apply it to a collection. What is a collection? I will take the collection of consisting of unions consisting of finitely many members from here. Okay, I will take all finite subsets of lambda, capital lambda. I will take the corresponding unions and take that collection. Okay, that is a collection of non-empty open sets, and that should have a maximal element, and my claim is that maximal element, which will be a finite union anyway by definition, will be all of X, and then I am done. Okay, so what I am going to do is put script S to be the set of all u lambda 1 union u lambda n such that lambda 1 through lambda m are elements of lambda, and m is an integer, m greater than or equal to 1. Take this collection. What I am doing is I am just taking finite unions from this collection, okay, and I am putting all these things together and getting this family of subsets. Then this, of course, this family of subsets is non-empty, okay, because of course my X is a non-empty topological space and there is at least one open set, and that one open set will occur here. Okay, this m could be 1, small m could be 1, in which case even the singletons are there. Okay, now since X is Noetherian, S has a maximal element. X has a maximal element. Okay, let that maximal element be, well, u lambda 1 union, let me call it, let me give some special names, lambda 1 prime to u lambda L prime, where lambda 1 prime through lambda L prime are all elements of lambda. Okay, so there is some finite collection of lambdas which I want to call lambda 1 primes through lambda L prime, and the corresponding open sets, and that finite union is a member in this collection, and that is the maximal element. Now take any u lambda, okay, then you see u lambda 1 prime union u lambda L prime union, if I put together this u lambda also, that will contain this element this maximal element lambda 1 prime union u lambda L prime. Okay, this is obvious because I have just I have taken union with a bigger set with another set, so this is contained in this. But mind you, this is in script S because this is also a finite union, okay, but this is supposed to be maximal. So what it will tell you is that this is equality. What is the property of a maximal element? The property of a maximal element is that if there is an element bigger than that, then it has to be equal to that. Okay, so this element is bigger than that, so it has to be equal to that. So this gives that u lambda is actually contained in u lambda 1 union u lambda prime 1 to lambda prime n. See, if this is equal to this, then this extra set I have taken union with has to be already contained in this, only then I will get equality. Okay, so but this u lambda I took was arbitrary, that the small lambda subscript I took was arbitrary. So what this tells you, this is true for all small lambda in capital lambda, so this tells you that x, which is the union of all the u lambdas, because all these u lambdas are a cover for x, that is also contained in this u lambda 1 prime union u lambda prime L, which is of course contained in x, okay, and this will tell you that x is actually the union of x is actually this maximal element, okay, and I am done. That is the end of the proof. I have proved that there is a finite subcover, okay. So this is how I get very easily that Noetherian topological space is always quasi compact, okay. Now I will give you another lemma. So here is another lemma, and what this lemma actually tells you is that the property of a space being Noetherian is a hereditary property, namely if a topological space is Noetherian, then any subset of that topological space given the induced topology also automatically becomes Noetherian, okay. So so let me write that down. If X is a topological space, is a Noetherian topological space, and Y in X is a subset, okay, then Y is Noetherian for the induced topology. Okay, any subspace of a Noetherian topological space is also Noetherian. That is in the property of a topological space being Noetherian is a hereditary property. Okay, now how does one show this? So that's the proof of that is also pretty easy. So proof. So you know I will have to show that y, so y is subset of x. I have to show that I know that capital X is Noetherian, I have to show that capital Y is Noetherian. So what I will have to do is for y I will have to verify DCC for closed sets, okay. So so what do? I take a descending chain of closed sets in Y, okay. Let T1 containing T2 and so on be descending chain of closed sets in Y, okay. Take a descending chain of closed sets in Y. Now what you do is you take closures of these sets in the bigger space X, okay. Then they are closures, then taking closures in X gives the descending chain T1 bar containing T2 bar and so on, okay. So I am taking closure in the bigger space X, okay. So what you must understand is that you see T1 closure is the closure of T1 in capital X, T2 closure similarly is the closure of T2 in capital X, and see T1 closure contains T1 which contains T2. So T1 closure is a closed set in capital X which contains T2, and therefore it has to contain T2 closure because T2 closure is the smallest closed subset of capital X which contains T2. That is how this descending chain gives rise to this descending chain, okay. But then what do you know about capital X? You know about capital X that it is Noetherian, and therefore this descending chain has to stabilize at some point. So since capital X is Noetherian, there exists an I naught such that T I is equal to T I plus 1 for all I greater than or equal to I naught. I have this. This is simply the definition of the Noetherian property. that you have if you have a descending chain, then it has to stabilize. Of course, you know, if I am assuming that the original chain is not a strict chain, if I had assumed it's a strict chain, then what I will then I will have to show that the strict chain is only, it terminates, it's only finite, okay, but I am not assuming that. What I am assuming is that I am not assuming that these containments are all strict, okay. So these containments also need not be strict, okay, and then I am just trying to use the Noetherian condition to say that it stabilizes at some point. Now what I want to tell you is that if this holds with the bars, then it also holds without the bars, okay. Why is that so? Because you see if you calculate ti plus 1, ti plus 1 is ti plus 1 is actually ti plus 1 bar intersection with y, okay. See, you take a closed subset of y, okay, it's not closed in the bigger space X, then you take its closure in X and then you intersect it with y, you will get back the closed subset y, because when you take closure in X, you are adding limits, you are adding the boundary even in X, which is in the bigger space, and then if you intersect it back with y, you are only looking at those boundary points in X which are already in y, but then the original set is closed, therefore it contains all its boundary points in which are already lying inside the subspace. Therefore ti plus 1 is ti plus 1 bar intersection y, but then ti plus 1 bar is actually ti bar intersection y, and that is equal to ti. This is true for all I greater than or equal to I naught, and I am done. So what I have proved is that the fact that the t bars descending chain, the descending chain of t bars stabilizes, implies that the descending chain of t stabilizes, okay. So that is the end of the proof of this lemma, which says that Noetherianness is a hereditary property, okay. Now apply both of these lemmas to the zariski topology, okay. First of all, notice that if I take affine space, any an is a Noetherian topological space, that we have already seen. That is just, as I told you, a reflection of the fact that the polynomial ring in n variables is a Noetherian ring, so any affine space is a Noetherian topological space. Now since it is a Noetherian topological space, any subset of an given the induced topology is also a Noetherian topological space because of this lemma, the second lemma, okay. And if you now apply the first lemma, that subset given the induced topology is Noetherian, implies that that subset is quasi compact. So what this altogether will tell you is that it will give you this proposition that you give me any subset of affine space, any subset of affine space, it will be quasi compact in the induced topology, okay. And that is what is meant by the statement that the zariski topology is quasi compact, okay. So you see, for any subset of affine space, quasi compactness is just comes for free, okay. It's nothing, it's not, it doesn't have the speciality that compactness, the usual compactness has for Euclidean spaces, okay. And that is the reason in a way that calling this kind of compactness, the compactness here as quasi compact, is kind of justified, okay. So when you say quasi, it means that this something is left out, okay, and in this case something serious is left out, okay. So how serious that is something that you will understand when we define what is meant by completeness or properness, which is the correct analog of compactness in algebraic geometry, okay. But for the moment that is the proof of this statement, okay. So now fine, so this kind of ends the discussion about open sets in the zariski topology. So the discussion, so let me summarize. The summary is that any open set in the zariski topology is a finite union of basic open sets, okay, and these basic open sets are very special in the fact that these basic open sets are actually themselves affine varieties, okay, they are isomorphic to affine varieties, okay, and you also have this property that the open sets in the zariski topology have the quasi compactness property, namely you give me any subset of affine space, if it can be covered by a collection of open sets, then I can extract from that a finite subcover. Okay, so this is about the open sets in the zariski topology. Okay, now what I am going to do is I am going to shift focus to something else which also was there in this discussion, and that is trying to define the so called functions on an open set of an affine variety. Okay, so you know, so the next part is defining functions on open sets. Okay, so of course when I say functions I will put it in quotes because what kind of functions we want is something that we have to decide upon. And so you know, let me recall. So what we did was if you take affine space and you take x inside affine space, of course small k is an algebraically closed field, and this is the affine n space with the zariski topology, and I am taking x a closed subvariety there. Okay, that is an irreducible closed subset there. So this is irreducible closed, and if you remember we defined the ring of functions on x, the so called affine coordinate ring, to be nothing but the affine coordinate ring of the bigger space, namely this which will be the set of polynomials in n variables modulo the ideal of x, okay, which is a prime ideal. So you know, this is an integral domain and it is a finitely generated K algebra, and then I told you that in this way we actually have a very deep correspondence which can be made sense of as a bijective correspondence or even as an equivalence of categories, okay, which goes on one side from affine varieties to the other side being finitely generated K algebras which are integral domains. Okay, so but the point is, for every irreducible closed subset this is the ring of functions we defined, and this is a very legitimate definition because you see what you are doing is the ring of functions on the affine space is defined to be just the polynomial ring in that many variables, because every polynomial in n variables can be thought of as a function on the affine space because you can evaluate it at each point of the affine space, it gives you a scalar. Okay, so these polynomials in n variables are certainly bona fide algebraic functions on the affine space, and then when you want the affine when you want the functions on a closed subset, an irreducible closed subset, then you have to go modulo the ideal of that closed subset, and that is because two functions on the full space, on the full affine space, two polynomials on the full affine space will define the same function on this subset, closed subset x, if and only if their difference is 0 on that closed subset, and that is the same as saying that the difference lies in this ideal. And so you have to identify functions modulo the ideal, and that is the reason why you are taking this quotient, and therefore you know this definition is absolutely fine. This definition is intuitively correct and it is also technically correct. Okay, so this is fine so long as you are trying to define the algebraic functions on an irreducible closed subset. But the question is, what are you going to do if you want to define algebraic functions on an open subset? Okay, and more seriously, in the spirit of analysis, how are you going to define a function to be algebraic at a point? Okay, see, what is it that we do normally in analysis? When we want to define continuity, you can define continuity at a point. Okay, if you want to define differentiability, you can define differentiability at a point. Similarly, if you want to define analyticity or holomorphicity, you can define it at a point. So all these properties you can always define at a point, alright, whether a function has that property at that point or not. Okay, so in the same way you can also ask in algebraic geometry, give me a function on some subset. Okay, when will you define it to be a good function, an algebraic function at a point? Okay, so this is in the spirit of analysis, how do you do this? Okay, so the clue is, so basically we want to study functions on open sets. Okay, so you know So the question is, if so here is the question, u inside an open subset, okay, or I'll let me say that after the statement. So take an open subset of an, and my question is, what is A of u? What is this? How do you define functions on u, right? And then more generally I can do the following thing: take x inside an to be an affine variety. So this is an irreducible closed subset, so this is an affine variety in an, it's a closed subvariety of an, and take u an open subset here, okay. Of course in all these cases I am assuming u is non-empty, because nobody wants to work with the empty set. Take a non-empty open subset, not in affine space, but take a non-empty open subset of an affine variety, and the question is, how are you going to define the good functions on u? How are you going to do this? How to define functions? So the key to this is the following, this is trying to look at, to try to define what are the functions on the whole open set, but now I can make it pointwise and say, give me a point of an open set. How do you define a function defined in a neighborhood of the point to be a good function, okay? So given, so here is the pointwise version. Here is a pointwise version. The pointwise version is given given p, given x, small x, in u, which is an open subset of x, which is an irreducible closed subvariety of an, okay. How do you, when do you say that a function v, a function, let me call this as f from v to k, where v is an open containing x, is good, is good, or by good I mean algebraic function, okay, a bona fide function, a function that comes in the algebraic sense, okay. How do you define a function to be algebraic at a point, okay? So the answer to all this is that, first of all, I can't keep always saying good all the time, and so we need a notation for that, we need a terminology for that, and the terminology is regular, okay. So we define good functions to be the so called regular functions, okay. We define the good functions to be regular functions. So my aim is, give me a point on an open subset, in an open subset of a closed subvariety, and give me a function defined in a neighborhood of that point, okay. When do I say that it is regular at that point, okay, that is my question. And how do you answer this question? The answer to this question is already there, we only have to dig it out. It is already there in the discussion that we have had so far. In fact, see, if you go back, we have already proved that any open set is a union of affine open subsets, okay, basic affine open subsets, okay. And therefore you can say that give me a point x and an open neighborhood of the point. This open neighborhood can be is a union of basic affine opens, and therefore one of the basic affine opens will contain this point, and therefore you can restrict the function to that basic affine open, and then I have to define what is a regular function, what is a good function on a basic affine open. But that I have already done. I have already defined what is meant by a regular function, a good function on a basic affine open set, namely it is just localization, it is the ambient ring of functions localized at that at that function. Okay, so recall if f is polynomial, then a of z of or rather a of d of f is defined to be equal to the polynomial ring localized at G at f. Okay, this is our definition. Okay, this is our definition. And what is d of f? D of f is supposed to be, it is the complement, it is an affine space minus the 0 set of f. It is open set given by the complement of the hypersurface defined by f. Of course, you know, if f is irreducible then you really get a hypersurface, but if f is not irreducible then z of f will be a union of hypersurfaces, those that correspond to the irreducible factors of f. Okay, and we have already defined a of d of f to be this of this form. Okay, and just so that I don't mess up notation, let me do something here. Let me call this as h. Okay, because I have already used f there. Let me call this as h and put h everywhere. And now you know what I am going to do. I am going to say that give me a point, give me okay, so I need to still make one more statement. This is for an affine open set it's a basic affine open set in the whole affine space. Okay, but I can also look at the basic of affine open set intersected with a closed subset. Okay, and it's not very difficult to see what the ring of functions on that will be. That's something that can be written down. So let me go to this side and do that. So it's again given by the appropriate localization. So you know, see if you take, so here is my an and here is my locus df dh. Okay, and the as far as the coordinate at the coordinate ring level, what happens is that if I apply this a this a function to this side, what I will get is I will get a of an, which is k of the polynomial ring in n variables, and here I will get a of d of h, which is the localization of this k of x1 through xn localized at h. This is what I will get. And of course, you know, this inclusion as an open subset shows up here as the localization map. This is the localization map. This is a natural map from a ring to its localization. Okay, and well, now if I take a subset x irreducible closed, if I take an irreducible closed subset x, then I can also look at dh intersection x, which is inside this. So you see, this is closed, this is open, and this is open. Okay, this is how the diagram looks. This is closed inside this because this is the intersection of a closed subset there, and this is open inside this, therefore this is an open inside this. Okay, by the definition of the induced topology. Okay, so the point is sometimes one can also write this as dxh. One can write it like this if you want. It is, and this dh will be dh in an. So this is t an k h. That's what this is. Okay, and you know what you're going to get here. What I'm going to get here is, see, this irreducible closed subset, this corresponds to this quotient going to the affine coordinate ring, the ring of good functions, regular functions on the ring of functions on x, which is just the polynomial ring divided by the ideal of x. Okay, and you know what this is going to be? this is just going to be the localization of this ring at the image of H here, which is H bar. So this is going to be simply k x1 xn modulo I of x localized at H bar, where H bar is simply the image of H here. H is here, it goes to the element H bar, okay. And if you actually look at it this way, it's a quotient by I, and this way also it's a quotient by I. This is a quotient by the Ix localized at H bar. So this is mod Ix, and this one is mod Ix localized at H bar. This is localization of an ideal at an element. So these two are quotients that correspond to these two closed subsets, okay, and these two are localizations. This is also localization. They correspond to these two open inclusions. This diagram commutes, this diagram commutes. That means this followed by this is this followed by this, this followed by this is this followed by this, okay. So this is what happens when you apply the A functor to this side. So what I want to tell you is that you already know what are the good functions on an affine open subset intersected with a closed subset, okay. So you already have definitions for what are good functions on affine space, namely the polynomial ring, what are the good functions on a irreducible closed subset, namely the polynomial ring modulo the ideal of that closed subset, which is the prime ideal, what are the good functions on a basic open set in affine space, it's just localization at that element which defines the basic open set, and what are the good functions on the the open set that you get by intersecting a basic open set in affine space with a closed irreducible closed subset, which is simply given by the localization of that corresponding, I mean it's just given by either the correct localization or the quotient in whichever way you want to see it, okay. So I am saying that we already have the value of this A for 4 kinds of objects. We have it for affine space. For affine space we know what are the good functions. For X we know what are the good functions for an irreducible closed subset. We know what are the good functions on a basic open subset of the affine space, and then we also know what are the good functions on the intersection of a basic open subset of affine space with an irreducible closed subset. Now from these 4 we have to cook up the correct definition of a regular function, okay, and the definition is obvious, but the surprise is the following. With this new definition, if you look at, so what you have done is you have defined regular functions at a point, and once you define it at a point you can define regular functions on any subset, okay. The moment you define it for a point you can define regular functions on any subset. So the question is, if I start looking at regular functions on the whole affine space, what will I get, okay. Will I get back my polynomials or will I get more? The answer is you won't get any more. That's the beautiful thing. Beautiful thing is on the affine space the regular functions will still be only polynomials. On the irreducible closed, on any irreducible closed subset, the regular functions will still only be these quotients, okay. You won't get anything more, and this tells you that your definition of regular function is correct, that your definition of regular function gives you the right thing when you for these known objects, okay. So I'll make that definition now. Definition let f from let f be a function defined on defined in a neighborhood in an open neighborhood of a point x in an affine variety, okay, or a quasi affine variety. Okay, a quasi affine variety is just open subset of an affine variety. Okay, we say f is regular at the point x if there exists polynomials f g with g not equal to 0 in a neighborhood, in an open neighborhood of x, and such that f is equal to I am sorry, I think I should use not f and g, I should use g and h, which with h not equal to 0 such that f is equal to g mod h in that open neighborhood of x. Okay, so look at this definition. This definition is this is what tells you when a function defined in an open neighborhood of a point is a good function, it is a regular function at that point, and it is very simple. All you are saying is that to say that the function, see the function is, when I say a function defined in a neighborhood of a point, it is a function with values in k, which is the field, scalar valued function. Okay, and all I am saying is that you can deem the function to be regular at a point if the function in a neighborhood of the point is a quotient of two polynomials, that is all. You are able to find two polynomials g and h such that the function you get by evaluating this quotient of polynomials is the same as your original function f in a neighborhood of the point, and that neighborhood of the point obviously should be in the locus where h does not vanish, otherwise I cannot evaluate. If h vanishes at a point, then I cannot evaluate g by h at a point because I will be dividing by 0. Okay, so it is a very simple definition. I mean it's a lot to write down, but the idea is very simple. You are saying a set theoretic function is good, is regular at a point if it can be written, if it is the same function as you get when you evaluate a quotient of polynomials in a neighborhood of that point. Okay, that is all. And what you must understand is that if your point is lying in a basic open set, then you know that the already the functions, the good functions you have defined on a basic open set are just localizations, the functions here. And what are the functions here? They are of the form g by h. In fact they are of the form g by h power n, where you also allow a power of, you do not only invert h but you also invert powers of h, because inverting h always automatically will also invert powers of h. So a general element here will look in the form, will be of the form g by h power n. Okay, but in any case it is one polynomial divided by another polynomial with the bottom polynomial not vanishing. That is how the functions look like, and you are saying that that is the kind of inspiration to define a general function to be regular at a point. And why is that inspiration correct? It is correct because every open set is always broken down into a finite union of basic open sets like this. In fact if you take any open subset in n, it is a union of finitely many dh for finitely many h, and if you take any open subset of x, a closed subvariety, that will also be a finite union of such dh's intersected with x. All this just follows because of the fact of that these are all Noetherian topological spaces, and therefore the subsets are all quasi compact. So any open cover admits a finite subcover. Okay, it just follows from that, right? Now I will have to justify that after, with this new definition of what a regular function is, I will have to show which is the amazing thing. The amazing thing is if you take affine space and look at all the regular functions in affine space, so I am looking at all functions on affine space that locally look like quotients of polynomials, okay, that looks a little bit more complicated than just looking at all the polynomials in n variables, but the fact is they are all the same. That is the surprise, and that is what I am going to prove. Okay, I am just going to show that this definition is correct if you take affine space or if you take a closed subset of irreducible closed subset of affine space. Okay, that kind of tells you that this definition is in the right direction. Okay, so I will stop here and continue in the next lecture.